Hello, welcome to this video mini lesson introduction to chi-square and contingency table analysis. The beautiful thing about chi-square is that it's incredibly versatile. You can use it with just about any kind of data, including skewed data, nominal data, etc. And the way that chi-square works is it's all about frequency counts, the actual number of cases that fall into different categories. Look, for example, at this data, and this comes from a study by Ingersoll and Orr way back in 1989, but they were looking at different factors that increased or decreased dropout risk. So here you see that risk looked at by gender, investigated by gender. And so you can see the number of males who fell into the high dropout risk category and low, and then the number of females that fell into the high dropout risk category and the low dropout risk category. And so these are actual number of cases, or in this case, students who fall into these different categories. And then what chi-square can be used is to determine whether or not there's statistically significant differences in dropout risk by gender, or in this case, by whether or not a student had ever run away from home. And so this is an example of the use of frequency counts as a mechanism for looking at whether differences are statistically significant or not. So there are a number of uses of chi-square and contingency table analysis. One is known as goodness of fit, and that's where you have only one variable with several different categories. It's also known as one-way chi-square, and here would be an example of that. This is a chart that we could complete if we wanted to investigate how fifth graders choose independent books by genre. So when fifth graders get to choose their own book, so a book for independent reading, we could look at how many students chose a book of each of these different genres, and then we provide the total here. This is what is called a one-way chi-square because we only have one variable. In this case, it's book genres. Now, if we have more than one variable, we're doing what's called a two-way chi-square. And for that, we do what's called a test of independence as opposed to a test of goodness of fit. So in our particular situation here, if we had wanted to break down these total numbers of students by genre and instead wanted to look at it by gender, then all we have to do is add another row here. And one of these rows would be female students, and the other one would be male students. And then we could look at the breakdown by gender as well. And for that, we would be using a test of independence because we have more than one variable. In this case, one of our variables, our dependent variable, is book genre. Our independent variable is gender. Now, in the Abbott text, he recommends that you put an independent variable in your columns and put the dependent variable in rows. We're doing the opposite here, and you will often see the opposite in real research. Also, another nice thing about chi-square is it can be used for hypothesis testing both in post facto and experimental designs. If you recall, ANOVA, for example, is really only used in post facto research designs, but chi-square can be used in both post facto and experimental designs. Now, if you're doing it for experimental designs, you would be doing either like a pre-post situation or a points in time situation where you would measure participants at one point in time, let's say fall of 2012, at a second point in time, let's say spring of 2013, maybe even a third point in time, say fall of 2013. Anytime you're doing pre-post or multiple points in time with the same participants, with the same cases, so to speak, you have to use repeated measures chi-square. So this is a special case of chi-square, and you can use McNamara's test if you need to do repeated measures with chi-square. And we might talk about this briefly in class, but know that that possibility exists. So when you're doing hypothesis testing with chi-square, your null hypothesis is simply going to be that your expected frequencies are equal to your observed frequencies. So in this particular case, I might compare how many students I expect to fall into each of these categories. Compare that with the actual number, the observed number of students who fall into each of these categories. And in a different video, we'll talk about how you figure out what are your expected frequencies. But for our purposes right now, just understand that when you're doing hypothesis testing in chi-square, you're comparing expected frequencies to observed or actual frequencies. And the null hypothesis would simply be that the two are statistically equivalent, that there's no statistical difference between them. The alternate hypothesis, as you may have already guessed, is simply that the observed frequencies and the expected frequencies are not equal to each other, that they are statistically significantly different from one another. The final thing that I want to say about chi-square right now is it can be used for parametric and non-parametric analysis. Now, parametric analysis, if you can recall, is where we're looking at a specific sample and we're trying to determine whether it comes from a population or whether it's so different from the population that it can't be said to be part of that population. In a non-parametric analysis, in this sort of situation, we're simply comparing, instead of a sample to a population, we're comparing observed to expected frequencies in this kind of a scenario. This ends our first video mini lesson. Now please go to the video mini lesson on goodness of fit. Thank you.